Hello everyone. So in this lecture, uh, I'm going to use large CVs to drive the mass and momentum conservation equations in integral form. So first we will derive the mass conservation in integral form, and then I will talk about fluxes in general and continuity equation, and after that we will similarly derive momentum equation in integral form. And in the next lecture, we are going to solve some examples of these using control volume specially, and using both continuity and momentum equation to solve some fluid mechanics problems. And after that, we will drive these momentum and mass conservation or continuity equation in differential form. So this is the overall kind of path of this class in the next few lectures. Okay, so now imagine we have this channel here. Imagine we have this channel here, and we want to write the mass conservation for this channel. So we know that mass conservation in a steady flow is as follows. So mass conservation in a steady flow, this principle states that mass that we have to, the mass that kind of, for example, enters into this channel and goes out of this channel should equal each other, right? This is kind of the mass conservation principle for this steady flow. But in order to write that, it's easier for us to use a large CV and write this mass conservation in terms of a large CV rather than, that is kind of an Eulerian approach, right? Where we have this field description. So the way I'm going to do it is I'm going to define a large control volume to calculate these mass that goes into and out of this control volume, and then write the mass conservation for that control volume. Okay, so just note that you are free to define any CV that you want, so it's kind of arbitrary. And this is the one that I'm defining it here. Okay, so this is my CV, a large CV, as you can see, a large control volume. And so here we have section 1 of that, and here we have section 2 where the flow goes out. So here the flow comes in, and then here flow goes out of the control volume. So the mass conservation principle in a steady flow, it states that mass that flows into the CV must leave the CV at the same rate. The same rate. Okay. So let's see what is the mass that flows into the CV. So here at section 1, we have the velocity of the flow is V1 and rho 1. And here at section 2, the velocity is V2, and we can imagine that or assume that the density is also changing as rho 2 to make it general. So over the time interval delta t, for a steady flow again, volume flow that goes into the CV is how much? Is the volume. We want the volume of that. So we have the area, the volume flow, we have the air. So let's see first. So here you have this amount is at delta t. If you imagine this is delta t, this is how much, let's say, water or any flow comes into the channel. So the distance or in this direction is going to be V1 delta t, right? And this is how much goes out of that. So we can say it is V2 times delta t, right? So V is delta x over delta t. So delta x is going to be V times delta t, right? This is just a side note. And now you want to calculate the volume of the flow that comes in. So this can have any section, right? So this can have any area. So this could be like a circular channel or a rectangular channel, but we know the area of that, right? So in order to calculate the area, so you have this area, say, and then we have this delta x. So let me, maybe I can do it very generally. You have this area, and then we have this delta x. So the total volume of that is going to be what? It's going to be A times delta x, right? Or here it's going to be A times V delta t. So I'm just going to write it down here. The volume flow in is A1 from here times V1 times delta t. And then the volume flow that is going out of this control volume is A2 V2 delta t over time interval delta t, okay? Okay. So now let's calculate the mass flow that is in. So mass flow in. So in order to get the mass of this, so mass, you need to just multiply rho density by volume, right? Which is AV delta T. So this is volume, and you will get mass. So I'm going to do the same thing. Rho 1, A1 V1 delta T. And then mass flow out, we have rho 2, A2 V2 delta T. So the conservation of mass says the mass flow rate that comes into the control volume and goes out of that should equal. Okay. So conservation of mass in a steady flow states that rho 2 A2 V2, and you divide it by delta T to get the mass flow rate, right? Minus the mass that goes in, which is rho 1 A1 V1 equals to 0. Okay, so this is the conservation of mass for steady flow. For a steady flow, so just remember that, because if you have an unsteady flow, then the flow inside your control volume might also change. So we have to consider for that as well. But imagine we have steady flow. And so this is going to be the conservation of mass that we can derive. We derived using a large CV. Okay. In order to derive a general equation for mass conservation or continuity equation, before that, I want to define the concept of flux and what do we mean by flux in fluid mechanics. Okay. So flux, because we are going to use this a lot in the course, and so I want you to understand it. So the flux of something, and it could be anything, for example, momentum, mass, anything, heat flux, heat, is the amount of that something being transported across a surface per unit time. Okay, so this is the definition of flux. So for example, you can have say you have a flow, a kind of a general flow field. So we have something like this. Okay. So in order to find the flux of this flow rate, the flux of this flow, so we need to first define a surface and then see how much of that something is being transported across that surface per time. So say I am going to define a surface like this. Like dA, and I want to see how much of that is being transported across this A, okay? So in order to simplify these, we define a normal vector for that surface, okay? So let's see what is that. So I'm going to first like zoom here. So say you have this so let me define it a little bit differently so you better understand. So it's an arbitrary shape, right? It could be any surface. So we have something like this here. So we have this surface here defined here. Say just I'm looking at this part. I want to see how much of the flow goes into across kind of is being transported across this dA. So this is dA. So what I'm going to define is what we call as the normal vector. So we define the normal vector, the vector that is normal to that surface. So it's normal vector. To calculate how much of that something is being transported across this surface. Okay, so now we calculate the volume across dA in delta t. So I want to calculate how much of that something is being transported across dA in time delta t. So here we have that surface, and then here we have the velocity. So the velocity vectors are like this, almost like this. So at time delta t, they are going like v delta t. This is going to be their delta x, right? How much of the flow is going into that, say, surface. Okay. And now, in order to see how much of it is going exactly inside that control volume, we need to calculate the normal vector here. So we have the normal vector. How much of it is exactly being transported into this surface. And here, what is this gonna be? So let me just plot it here, this vector. Let me make sure they are. We can zoom here to better see that. So if this angle is theta, this is theta, and this is also perpendicular to that. So this is gonna be V delta t times cosine theta, right? Okay, so now the volume that is being transported into this is V delta T cosine theta times, this is going to be actually that delta X, and then you need to multiply that by dA to get the volume. So this is the volume across dA in delta T, okay? So we have a conversion for this V delta T times cosine theta. We can write it in terms of the normal vector. So this can be written as N, the dot product between the normal vector and the velocity vector. And then you just multiply it by delta T. So from your calculus, if you have two vectors, the dot product of them, A dot B, is gonna be AB cosine theta. Okay, so that's exactly what we have here. The normal vector, its magnitude is 1. So N dot V is going to be normal vector N, its magnitude, times V times cosine theta. So this is just 1 because it's a normal vector, and this is how we define it. So you are just going to get V cosine theta, right? So A and B could be like this. This could be A. This is B. And this is theta. Okay. And A dot B is going to be their dot product. Okay, so this is something from calculus and algebra that you need to know. So we can define this as N dot V times delta T. Okay, so I can just write V delta T cosine theta times dA as N for any general thing based on the normal vector as N dot V times dA times delta T. Also, we have a convention here that the volume, first of all, one convention is we always define the normal vector toward outside of any control volume. So if we have something like this, the normal vector, we always define it toward outside. Okay, so this is the first convention we have, and you need to remember. And the other one is that volume out, the volume that goes out is always positive, so we always take it as positive, and the volume that goes into the control volume or into the surface is negative. The sign of it is negative, okay? So based on these definitions, now I want to define flux, which is the amount of something that is being transported across a surface per unit time. Okay. So let me define the flux here. So we can define first volume flux. So the volume flux is what we just actually derived here. So this is volume across dA in delta T. So in order to calculate the flux of volume, the flux volume, we just need to see how much of it is being transported across A per unit time. So we just need to divide this by delta T to get the volume flux. So it's just going to be N dot V dA. Similarly, we can define mass flux. So in order to define mass flux, we just need to multiply the volume by density. So we just do that by this. So it's going to be N normal vector times rho V, which is density, times V times dA. We can similarly define momentum flux. So in order to define momentum flux, you just need to multiply M times V, right? So this is going to be momentum. So it's going to be N dot rho V, which is mass, times V. This is going to be momentum times dA. So this is momentum flux. And similarly, we can define a lot of other kind of fluxes like heat flux or even kinetic energy flux. So kinetic energy flux. So it's just mv square, kinetic energy is mv square over 2. So we can define it like that. So it's going to be m, which is N dot rho V times V square times dA over 2. Yeah, I think it should be over 2. And so these are all the flux definitions that we can define. Okay. So now I'm going to use this concept of flux in order to drive the continuity equation and momentum equation in integral form. So I'm going to do this in the second part of this lecture.